Today, we want to look at the ambiguous case of the law of sines, the side-side angle case. There's been some question about how we determine the number of triangles before we begin. Remember, we don't need to know before we begin. We can just kind of like blindly walk into the law of sines, and the numbers will tell us when we have 0 triangles, or 2 triangles, or 1 triangles. Or 1 triangle, but it's really hard to land. If we're looking at a right triangle, that should probably, that'll show up pretty quickly. So let's talk about the ambiguous case of the law of sines. Here's a set of information. I've got side B, angle gamma, and side C. So I have a pair of opposite information. I have side C and angle gamma. I have 2 sides and the angle opposite one of those sides. So this makes now we're aware we're in the ambiguous case of the law of sines. We're in the side-side angle because gamma is opposite one of my given sides. So let's identify the parts. So C is the side opposite the given angle. Gamma is the angle, is the given angle. Suppose I should label that too. And then in kind of a rude, dismissive way, I always call, in the side-side angle case, I have the side opposite the given angle, and then I just label the other side the other given side. It's kind of rude, but it's just a side in a triangle. It's not like it's a person that I'm dismissing as some other or making it related to something. So this is the other given side. So I've got the side opposite, the given angle, and the other given side. This says ambiguous case of the law of sines. Remember, just starting off, we use whatever we can. And since I have a set of opposite information, an angle gamma and side C, that tells me it's the law of sines. But we are in the ambiguous case because we only have one angle, and we're in the law of sines. To calculate the height, the number of triangles is determined by how the side opposite compares to the height of the triangle. The height of the triangle is always going to be the other given side multiplied by the sine of the given angle. So the height is the other given side multiplied by the sine of the given angle. So you take the comparison always is how does the side opposite the given angle compare to the height of the triangle? The height of the triangle is based on the other 2 things, the other given side and the given angle. So the number of triangles is determined by how the side opposite the given angle compares to the height of the triangle. So the number of triangles is determined by comparing the side opposites to the height. The number of triangles is determined by comparing the side opposite to the height. So we'll compare the side opposite the given angle to the height. In this case, the height is going to be 12. 12, take the other given side and multiply by the sine of the given angle. So we grab our calculating machine. We make sure we're in degree mode. And then I calculate 12 times the sine of 43.2. So the height is 8.21. The side opposite the given angle is greater than the height, but less than the other given side, so we'll have two triangles. There are four things that can happen, one of which is really hard to land on. But in this case, we see that the side opposite is greater than the height, but less than the other given side. So the side opposite is greater than the height, but less than the other given side. And so that tells us that we're going to have two triangles. So when we find that first angle, when we're doing the law of sines, the ambiguous case of the law of sines, the first thing that we're going after is an angle. Since we know that there are two triangles, we just find that the angle that we get from the sine inverse in the first and second quadrants. So the next thing to do would be to set up sine of gamma, set up the law of sines, 43.2, sine of 43.2 divided by 10 is equal to the sine of beta is the first angle that we're going to be going for, divided by 12. So beta is going to be the sine inverse of 12 sine 43.2 divided by 10. What we're doing is we're taking the sine inverse of the height divided by the side opposite. So if I take the sine inverse of the height, 12 sine 43.2 is what I have as the answer, and divide that by 10. So the sine inverse of the height divided by 10 is 55.2 degrees. This is our first value of beta, but since we're in the two triangles case, we need to find the other beta in quadrant 2. This is the quadrant 1 angle. Since we're in the two triangles case, we need the beta in quadrant 2 as well. So a 55.2 degree reference angle in quadrant 2, our other beta is 180 minus 55.2. 124.8. So we got two values for beta, one in quadrant 1 and the other one in quadrant 2. Once we have two angles, a gamma and a beta, the problem is now split into two parts. I've got to do one, excuse me. On one side, I've got to find my alpha by subtracting. I have two angles, so I subtract to find the third. 180 minus 43.2 minus the 55.2. So that is an 81.6. There's our first alpha, but then we're going to have another alpha to go with the other beta, because we're in two triangles land. So we'll subtract the 43.2, and we'll also subtract the 124.8. And we get a little tiny 12-degree angle. If we were not in the two triangles case, then when we try to, one thing that might happen is that we try to subtract this to find the second alpha, and this ends up being negative. If your alpha ends up being negative, go back and double check. Maybe you're not in the two triangles case after all. Or maybe that's what you were waiting for to determine. Once we have that alpha, we need to use the law of sines again to find the last side. I've got first beta, first alpha, so now I need to find A. So I need to take the sine of 43.2 divided by 10 is equal to the sine of alpha, which is 81.6, divided by A. So here A is going to be 10 sine of 81.6 divided by the sine of 43.2. Note that we're not using a sine inverse here because we're not looking for an angle. But I am going to be using rounded off information. So 10 sine of 81.6 divided by the sine of 43.2. So 14.5. So yes, we could at this point, I used gamma and C because that was the given information. But we could grab the 55.2 and then assign 55.2 divided by 12, and then divide that by the sine of, oops, sorry. I could do 12. I could set up this ratio as the sine of 55.2 divided by 12 is equal to the sine of 81.6 divided by A. So that would mean instead of 10 sine 81.6, I could have done 12 sine of 81.6 and divided that by the sine of the 55.2. So instead of using gamma, we can use beta. And we still get the 14.5. I try to use original information because that's the stuff that's given, and the 55.2 has been rounded off. For the most part, it won't make a difference. You're not going to be wildly off unless you're doing a really bad job of rounding, like rounding 14.5 to 10. That'd be going too far. So yeah, but that's a great question. We can use whatever, the law of sines, we have those three choices. Once we have an abundance of information, we've got two of those fractions. We can use any one to find the third fraction. Over here, we'll set up sine. We have to find another A because we have another alpha. So I take the sine of 43.2 divided by 10. So I'm going to use gamma because that was given information. And this is equal to the sine of 12 divided by the other value of A. So the other A will be 10 sine of 12 divided by the sine of 43.2. So my other A will be 10 sine of 12 divided by the sine of 43.2. So my other A is 3.0, we'll call it. I'm rounding everything to the nearest tenth for some reason. There we go. But just like before, instead of using 10 and 43.2, that is C and gamma, we could do 12 sine of 12 and divide by the sine of 55.2. That is, use beta and B. And we still get the 3.0. We have to go pretty deep to see how different they are when I use the non-rounded stuff versus the rounded stuff. Because the only thing that we're rounding is the 12. But we did have two triangles because the side opposite the given angle was greater than the height and less than the other given side. That's where we determined the number of triangles. Notice that what we're looking at is the ratio of the height. We're doing the sine inverse of the height divided by the side opposite the given angle. If the side opposite the given angle is less than the height, then we have no triangle. And the sine inverse will tell us that, because the height, if the height is greater than the side opposite the given angle, then we'll try to find the sine inverse of a number greater than 1, and we'll get no angle. No angle has a sine that is greater than 1. So let's look at an example like that. Let's suppose that B is 12, gamma is 43.2, and side C is 7. Once again, we want to identify the case that we're in. I have C and gamma. I have a set of opposite information. That indicates law of sine should be used. And I have another side. So that tells me I'm in the ambiguous case of the law of sines. So I'm going to identify C. It's opposite the given angle. So this is my side opposite. That's the side opposite my given angle. And 12 is my other given side. I'm labeling things this way because we've already identified that we're in the side-side angle case, the ambiguous case of the law of sines. Let's suppose that we want to know, before we start doing any law of sines, the height of the triangle. So the height of the triangle is the other given side multiplied by the sine of the given angle. So in this case, that would be 12 times the sine of 43.2. We just calculated this, but because it's on the other page, I can't look at it, and I don't have a memory that will remember this. So I'm just going to calculate it. 12 times the sine of 43.2. So the height is 8.2. In this case, the side opposite the given angle is less than the height, and that means there is no triangle. So the side opposite, 7.0, the side opposite is less than the height. That means there are 0 triangles. Which is kind of awesome. That means that we are done. No triangle. So remember what this looks like. So here's how we remember it in things like formulas or statements. The side opposite the given angle is less than the height, then we have no triangles. We also might want to visualize this. So here's the line where the third side is going to be. So if this is the line where the third side is, I want to draw the given angle and the other given side. They're going to be connected to each other. So here is the other given side, and here is the given angle. So by drawing this, we can visualize why we calculate the height this way. The height is going to be the shortest distance from the other end of the other given side to the line where the third side should be. So we're building this right triangle. We're trying to build this right triangle, and that's where we're going to find the height. That makes sense. That's just right triangle trigonometry that we learned in like the first week. Set the Wayback Machine to right triangle trigonometry, and we'll land right here. So with right triangle trigonometry, we can see that the height is, well, we could say that the sine of the angle is opposite, which is the height, over the other given side. So if I set up a trig ratio, the sine of the angle is the opposite height over the other given side in a right triangle. Because the other given side is the hypotenuse. So here's where we can solve for the height by multiplying by the other given side. So that's why the height is the other given side multiplied by the sine of the angle. What's happening when the side opposite the given angle is less than the height is that the side opposite the given angle is too short. I can't connect this end of the other given side to the line where the third side should be. The side opposite is too short. And that's how we think of this, the zero triangles case. The side opposite is too short. The side opposite is too short. It's not long enough to cover the height. The height is the shortest distance from the other end of the other given side to the line where the third side should be. So if I try to draw the side opposites, it's not long enough to connect the other given side to the line where the third side should be. It's too short. It wishes it was a little bit taller. Wishes it was a baller. That reference might go a little bit too far back. Difficult thing with Zoom is I can't just kind of like scan the class and kind of get a rough idea about how old everybody is. So I just have, all I have is the other information I have to go on. It's a trig class. It's in the spring semester. My guess is that my just general idea is that most of you is like 1 year or 2 years out of high school. You know what I mean? Yay, I'm glad someone recognizes it. All right. It's one of those things though, as like an aging teacher, I need to update my references, but at a certain point, it just be like when an old teacher like updates the references, at a certain point it just becomes kind of sad. The last thing I would ever want to do is walk into the classroom and actually try to talk like young people talk. Just talk like you're going to talk. Do you know what I mean? So I guess my point is, if you're a square, just lean into being a square. And if you don't know what being square is, then that's okay. That just means you're younger than I am. All right. So the other thing that could happen, we've only got a few moments left. So what happens is the other given side If the side opposite the given angle is less than the height, it's too short. It can't reach the line where the third side needs to be, so we can't make a triangle. If the side opposite is exactly equal to the height, that's when they're the same. So that's where we're going to get one triangle. That's hard to just build without just straight up cheating and stuff like that. But it's possible. If the side opposite is equal to the height, then we'll have one triangle. When the side opposite the given angle is a little bit longer than the height, then we'll get two triangles, because I can think about the previous case where the side opposite was 10, so it was more than the height. So I can make two lines that connect the other given side to the line where the third side should be. I could draw one here, make an obtuse triangle, and draw one on the other side to make an acute triangle. Now, if we think about the other given side swinging between the height, so think about that side and then another equal line over here. If I make the side opposite the given angle greater than the other given side, then this one that swings inside is not going to be able to hit and build a triangle over here. And that's why we're going to end up with this angle that we look for first being negative. And we're just going to get the one that stretches way out over here. So those are the four cases. We can have zero triangles if the side opposite is less than the height. We have exactly one triangle when the side opposite is equal to the height. We'll have two triangles if the side opposite is greater than the height, but less than the other given side. And we're back to one triangle if the side opposite is greater than the other given side. So if I set up this problem with a 12 for B, gamma is 43.2, and C is 17, I wouldn't even have to worry about the height. The side opposite is greater than the other given side, so we'll have one triangle. So once again, wanted to go over this because there's been some question about how to determine the number of triangles that you have in the ambiguous case of the law of sines. All right, that's going to do it for today. That's going to do it for this week. Make sure that you're all caught up on all your homework and your quizzes on Canvas. I'll see y'all on Monday, and thanks for playing.